everybody, and welcome to Unit 5, Lesson 6, which is about absolute, or in other words, global extrema. Now, we have one learning target for today, and that is going to be I can use the candidates test. So that's the name of the test we're doing today, to determine the location of the absolute, or sometimes we call those global extrema, of a function on a closed interval. Now, here's what's really important. I want you to think back to when we first started talking about relative maximums and minimums. We said, hey, you can use the first derivative test or the second derivative test to find relative maximums and minimums. Today is the day where we're adding in global or absolute maximums and minimums. So let's talk about that definition, and then we'll talk about how to find them. Unlike a relative minimum, a function has an absolute minimum if there is a point that is the lowest the graph will ever go. Now, I said if there is a point because it is possible that there's not an absolute minimum for a function. There are some functions that are going to go down, down, down forever and ever and ever, and they're never going to reach a lowest point, in which case there is no absolute minimum. It is also possible that an absolute minimum could occur at an endpoint of an interval. So sometimes if we decide to restrict the domain of a function and we say stop when you get to this point, even though potentially it could keep going, we're forcing it to stop, it creates a place on the graph where you reach the lowest point because the graph stops. And so let's look at some examples. So let's look at the absolute minimums for these graphs. So again, the lowest the point is ever going to go. In this first picture, the absolute minimum would be right here, because that would be the lowest the graph is ever going to go. So we would say that the absolute minimum value here is negative 2 point something. I'm going to call it 2.1 at the place where x is equal to, I'm going to call it 1.2. Now you'll notice I did not just list an ordered pair here. I didn't just say it's the point 1.2 comma negative 2.1. I'm saying the absolute minimum value is 2.1. So this number right here is the value. It's how low does it go? And the x equals 1.2 is the location. This is the where does it happen. So when we are asked to find the absolute minimum, we usually say the absolute minimum value is negative 2.1. That's the lowest it goes at x equals 1.2. We don't usually write it as an ordered pair. Let's look at the next picture. So this is the graph of a nice cubic function. And if we were just to graph a normal cubic function, we would expect it to kind of keep going forever and ever and ever and have arrows. But in this case, we have kind of forced the graph to stop by putting points on the ends. What that meant was that instead of going down forever and ever and ever by kind of following this graph, the graph stopped. So even though this graph would maybe not normally have a lowest point because it would go down forever, by forcing the graph to stop, we created an absolute minimum. The absolute minimum on this graph would be right here, because by putting an end point there, by stopping the graph, we created a point that is the lowest the graph will ever go. So we would say that the absolute minimum value is negative 2 at the place where x is equal to negative 5. Now, on this last graph, I want you to know that the intention here was that this graph keeps going forever. That's why the graph goes to the edges and never stops. So you can imagine that there's little arrows there. In this case, because the graph is going to keep going down, down, down forever, there is going to be no absolute minimum. You're never going to reach a point where the graph is the lowest it ever goes because it's going to go down forever. So we would say none here. Now, just like we can find an absolute minimum, it is also possible to find an absolute maximum. An absolute maximum occurs if there is a point that is the highest the graph will ever go. Now, again, I said if, because it is possible that there is not an absolute maximum. It just depends. Like, does the graph keep going forever, or does it actually have a highest it'll ever go spot? It is also possible that the absolute maximum could occur at an endpoint. So, unlike relative maxes and mins, absolute maxes and mins can occur at endpoints, whereas the relative maxes and mins, we said no endpoints allowed. So, if we look at these graphs and we want to find the absolute maximum, this first graph, the absolute maximum would be like right here. So, we would say that the highest that this graph goes is maybe 0.5, and that would occur at the place where x is negative 0.5. In this next graph, just like this endpoint became the absolute minimum, this endpoint is going to be the highest the graph ever goes. It's never going to pass that. So this is going to be your absolute maximum, which is going to be a maximum value of 3 at the place where x is 4. So the highest this graph is ever going to go is 3, and that occurs at the place where x is 4. And last but not least, in this graph, because of this arrow that keeps going forever, we would say that there is no absolute maximum. It's never going to get to the highest spot because it never goes past there. So we would say none. Now, how can you find these values if you don't have a graph in front of you? To find these values using information about a function, we use something called the candidates test. So if you think about like an election, you look at the list of candidates and you evaluate them, you determine who's the best one, and then that's who you choose as your vote. That's what we're going to do here. We're going to make a list of all the possible places where the graph might have a highest or lowest spot. And then based on the information we find out about those locations, we're going to choose the highest and the lowest out of that list. First, we're going to start by finding the critical points of f of x. Just as a reminder, that's going to be places where the first derivative is equal to 0 or the first derivative does not exist. Then we're going to make what's called an input-output table of values. So if you think back to when you first learned how to graph, you made table of values where there was x in this column and y in this column. And we're going to make that table of values, including the endpoints of the interval that we're given, if there is an interval, as well as the critical points that we found in step number 1 in the table. So in this table, in the x column, we're going to have our endpoints, and we're going to have our critical points. Then we're going to plug those numbers in. We're going to find the y values, and we're going to say, okay, who's the highest and who's the lowest? Because the highest one is going to be the absolute max, and the lowest one is going to be the absolute min. Let's go through this process. So let's start by finding the critical points. So I'm going to take the derivative of this function, which is 4x cubed plus 12x squared, and I'm going to set that equal to 0. I'm going to factor out a 4x squared, so I get x plus 3. And then my critical points are going to be when x is 0 and negative 3. Next, I'm going to make an input-output table of values. So I'm going to have x and f of x. In this table of values, I'm going to include the endpoints, which are negative 2 and positive 1, as well as the critical points, as long as they're between the endpoints. So you'll notice here we have 2 critical points, 0 and negative 3. However, 0 is not between the numbers negative 2 and negative 1. So negative 3 is not between the numbers negative 2 and negative 1. So I'm not going to include the negative 3 in my chart because it's not part of the interval that I'm looking at. So I'm going to put the negative 2 here and the positive 1 here and the 0 in between. Now I'm going to find my function values. Now you'll notice I'm finding f of x. So the actual y values or output values of the original function. Now, this is different than what we're used to doing. We usually plug our numbers into the derivative. However, what we're doing is we're looking for the actual how high or how low does it go. So we want the y values of the original function. So f of negative 2, which is this first number I need to plug in, would be negative 2 to the fourth power plus 4 times negative 2 to the third power. Now, negative 2 to the fourth power is 16. Negative 2 cubed is negative 8 times 4 is negative 32. And so I'm going to get negative 16 here. To find f of 0, I'm just going to plug in the number 0. So I'm going to have 0 to the fourth power plus 4 times 0 cubed, which is 0. And lastly, I'm going to plug in the number 1. So f of 1 would be 1 to the fourth power plus 4 times 1 to the third power, which is going to be 1 plus 4, which is 5. Now, out of this list of numbers, we can find the highest and the lowest. So since the negative 16 is the lowest, this is going to be the absolute minimum value on this particular interval. And since the 5 is the highest number, this is going to be the absolute maximum value on this particular interval because those are the lowest and again the highest numbers. So our answer would be that f of x has an absolute minimum value of negative 16 at x equals negative 2. So the minimum value is negative 16 at x equals negative 2. And f of x has an absolute maximum value of 5 at x equals 1. So the highest it goes is 5, and that happens when x is 1. Now, one thing that I think is worth pointing out is that for most of the stuff that we've learned in this chapter, we have always started by looking at a function and figuring out how to do the problem, and then looking at the graph of the derivative and figuring out how to do the same thing using the graph of the derivative. It is important to note that right now, we do not have the mathematical tools in order to find the maximum, the absolute extrema, using the graph of a derivative. So that's why it's not in your notes. We don't know how to do this yet, and we don't have those tools yet. We will revisit this idea when we learn about the concept of integrals. Once we know how to integrate to find the original function values or to use an integral to find the original function values using the derivative, we will be able to find absolute extrema using the graph of the derivative. We just don't have that tool yet. What I'd like to do now is summarize the 3 different tests that we have that help us find extrema. And these tests might help us find relative or absolute extrema. The first test that we learned about was the first derivative test. And what this does is it uses the sign of the first derivative to identify relative extrema. It does not help us find absolute maxes and absolute mins. So it's important to note that we do not use this for absolute maxes and absolute mins. And that we do not include the endpoints. When we are looking for relative extrema. What we learned in this test is that if the first derivative changes from positive to negative, then the original function has a maximum. And if the first derivative changes from negative to positive, then the original function has a minimum. The second test that we learned was called the second derivative test. And this, again, is going to help us identify relative extrema. So the same rules applies. It does not help us find absolute maxes and mins. It does not include looking at the endpoints of an interval. This uses a combination of the first derivative being equal to 0 or undefined and the sign of the second derivative in order to identify relative extrema. If the first derivative is equal to 0 or undefined and the second derivative is positive, then we have a function that's concave up and we must be at the bottom, so our original graph has a min. If the first derivative is equal to 0 or undefined and the second derivative is negative, then our function must be concave down, we must be at the very tippy top, and therefore the original must have a max. The last test we learned, and this is the one we learned today, so we're probably not going to be quite as familiar with this because we haven't practiced it yet, is the candidates test. This is the only test that we have that allows us to identify absolute extrema. So if I ever ask you to find the absolute max or the absolute min, this is the only way to do that. And this is going to be when we use the function values, which are the outputs, at the critical points and the endpoints. So this is the first time and the only time we include the endpoints as our candidates. That's going to help us find where the highest of the highs and the lowest of the lows would be located. All right, thank you guys so much for watching. That's it for today's notes, and I will see you soon for some practice.